In this video, we're going to learn more about the aldehyde and ketone reactions, but with stronger nucleophiles. So carbon, nitrogen, hydrogen nucleophiles, and then we'll do a couple of the oxidation reactions. So you've seen this before, or maybe you have not, but in any case, if you have any kind of an aldehyde or a ketone, it will easily undergo nucleophilic addition reactions. So here's the nucleophilic addition going on. So a strong nucleophile will attack the delta positive of the carbonyl, and then you end up getting the electrons pushed over to the oxygen to give the oxide. So the nucleophile attaches here to the carbonyl carbon, and then the oxygen is protonated to give the alcohol. So a few things over here that I just want to remind you of, because now we will be working a lot more on this kind of reaction, is that you're going from an sp2 carbon to an sp3 carbon, right? So I've written that over there for you. You go from a trigonal planar to tetrahedral. So again, all of these things you have to keep in mind as we go through these reactions, because in some cases chiral center is generated, in which means you can also get enantiomers. Okay, so these are just some things to keep in mind. One of the things I want to just kind of mention over here for us is that the nucleophiles we'll be using in this video, this one will all be strong nucleophiles. Okay, no more of the weak nucleophiles. The weak nucleophiles would be if we were using a acidic medium and oxygen nucleophiles. Okay, but these ones are going to be strong nucleophiles. In this case, aldehydes and ketones react equally well. There is nothing like, that aldehydes will react faster than ketones here. No, they are just, they still are more reactive, but here both of them will react equally well with the strong nucleophiles. So here again is the list of all the nucleophiles that we have for aldehydes and ketones, all the reactions. So oxygen nucleophile, I covered this in the separate video, and that was the oxygen nucleophiles with these two. And the reason these two are separated out is because they are done in acidic medium. And here the oxygen of the carbonyl is the nucleophile. Okay, so it's a little bit different. And now what we are talking about with all the other nucleophiles is that you're adding a nucleophile and the carbon is the electrophile. Okay, the carbonyl of the carbon is the electrophile. So we've got a whole lot of nucleophiles here to do. Some you have done before, some you have not. So we will get started with the carbon nucleophiles first. And in the carbon nucleophiles, Grignard reagents, I don't know how many times we've done this already, but we'll just do this really quick so you have a good review. But Grignard reagents, as you know, are very, very common for making alcohols. And the way you make any kind of a Grignard reagent is by taking any alkyl halide, treat that with magnesium to get the reagent. Now, the reagent you make has to be used up right away because it's very reactive. Okay, so you use up the Grignard reagent with the carbonyl compound in order to make the alcohol. Okay, we're going to get there in just a second. But some of the other reagents that we can also use for as a carbon nucleophile, and these are not necessarily called Grignards, okay, but they're very similar to Grignard. See, they're just organometallics, you can call them, is a lithium reagent, and the lithium reagent is made the same way. You take an alkyl halide and you treat that with lithium, and you get a lithium organolithium compound. Okay, and then alkynes also can be generated into alkanide, a good nucleophile. So you've done this reaction before as well. The only one we may not have done so much before is lithium reagents. Excuse me. Okay, sorry about that. So this is the only one that we have not done so much, but all the other ones we have. Okay, so hopefully it's a good review for you to go through all of these again. Okay. Okay, so here's the Grignard. Okay, and then reaction with formaldehyde, an aldehyde, and a ketone. Okay, so if you take Grignard reagent with formaldehyde, you will end up getting a primary alcohol. Okay, your Grignard reagent can be as big as you want, as small as you want, but your aldehyde is limited to formaldehyde in this one. Formaldehyde meaning only one carbon, all right, methanol. So this one is going to give you a primary alcohol with however many carbons, it doesn't matter, all right. Two-step reaction, one with the Grignard, second is protonation, not together, two steps. And then here is Grignard with an aldehyde with any other aldehyde. And then you end up getting a secondary alcohol. And a Grignard with a ketone will give you a tertiary alcohol. So this is something we've done before. The mechanism is pretty straightforward. You can go back to the alcohol video and see how we made alcohols, because this is all synthesis of alcohols. But this is reactions that we are doing right now. So reactions of aldehydes and ketones, same thing. Just a different perspective now, right? So, but anyhow, the good thing about the Grignard reactions with aldehydes and ketones is you get a variety of alcohols. You can make any kind of an alcohol you want to in good yields, okay? So I've tried again to color code things for you, so hopefully you can see which fragment is coming from where. So here are the other organometallics. And the mechanism is given here slightly to you. The only arrow that I have not written out, I mean, I can show you, but I mean, it's a simple one, which is, the oxide picking up a proton to become protonated to give you an alcohol. Other than that, everything else is fine. So you can see here, you can take whatever organolithium reagent you want. It's going to work the same way and you still get the alcohol. The alkanide nucleophile, exactly the same thing. So again, you treat that with the carbonyl, you end up getting an alkyne. So depending on what you want, do you want an alkyne on your compound or do you just want an alkyl group, okay? Now, the difference between the organolithium and the Grignard reagents is the organolithium are, just way more reactive, okay, than Grignard reagents. And so they're a little bit harder to control, okay? But otherwise, they're good, okay? No problems at all. Generally, people like to work with Grignards because they're more controllable and less hazardous also. Lithium can be very hard to work with, so it's much easier to work with magnesium, okay? Otherwise, you're still getting an alcohol. Now, in the case of alkanide, things are a little bit different because you're getting an alkyne also, okay, as there. So if you wanted a functional group, you have an additional functional group, okay? So that's that. All right, so another carbon nucleophile that we can add is a nitrile group. So CN is a nitrile in organic chemistry, but otherwise you would call it a cyanide group in Gen Chem or in organic chemistry. So CN minus, that's the group, okay, that you're adding here. So how do you get the CN group? How do you get a cyanide group? Sodium cyanide, potassium cyanide. These give you a very good nucleophile, right? Because this is an ionic bond. So the nitrile or the cyano group here is a good nucleophile that can work. So HCN, on the other hand, is fine, it can work, but first of all, it is a little bit less reactive and definitely a lot more toxic. This is a gas. Sodium cyanides and potassiums are, salts, so they're solid, okay? So it's a reactivity thing and nothing else, and toxicity thing. Of course, we are all careful about that. Even cyanides in general are a little bit hard to work with, so they're toxic. You have to be careful with them. But what is the reaction? The reaction is that the cyanide will attack the carbonyl. Again, same thing. You get the oxide. Oxide picks up a proton. You end up getting an alcohol. So here, this is what you end up getting, okay? A cyanohydrin. The cyanohydrin itself is not really the final product for a lot of reactions. You generally take this one and then you convert it to something else because the cyano group itself is not very useful, okay, in general, like by itself, all right? But you can take this nitrile group and you can convert it to something else, okay? What can you convert it to? You can transform it or convert it into different kinds of things, okay, depending on what you want to do. So you take a nitrile group, and if you treat that with dilute acid, you can hydrolyze that to give you carboxylic acid, Okay, so this reaction we're doing now, and we will do it again when we get to carboxylic acids. So cyano group, okay, again a nitrile group can be converted into carboxylic acid. If you treat this with sulfuric acid, so you're doing two things over here. You're first of all, you're doing the hydrolysis on the nitrile group to give it carboxylic acid, and then you're also dehydrating the alcohol group, because the alcohol group can be dehydrated by strong acids, right? So again, here just remember to make a Zaitsev product, okay? More substituted alkene. Other than that, it's all fine. So two things happening here, okay? Dehydration also. So it depends. Do you want to keep your alcohol? Do you want to get rid of it? It's up to you. And then finally, if you take the nitrile and you reduce it using a strong reducing agent like lithium aluminum hydride, you end up getting an amine. Okay, so you can see like it's a versatile group, okay, to do other things by itself, not so useful, but can be used to convert to other groups in there, okay? The interesting thing about the cyanohydrins is that you're adding a carbon, okay? I mean, with the Grignards, also you're adding carbons, right? It's a carbon-carbon bond formation. So here also you're adding a carbon. So that's an interesting part about all of these nucleophilic reactions. The third nucleophile for carbon is the Wittig reaction. The Wittig reaction is an awesome reaction. It works beautifully, and also it's a very simple reaction if you look at it. Okay, so here you have a Wittig reagent, which is also called the Yelid. So you have the Wittig reagent, which can react then with the aldehyde or ketone. It doesn't matter which one it is. And whatever you have on the Wittig reagent, whatever alkyl group you have on the Wittig reagent gets exchanged for the oxygen. So this is not an addition reaction. You see that? This is more like a substitution. So if it was an addition, you would get sp3, right? A tetrahedral carbon, but this is not tetrahedral. You still have the alkene. So all you're doing is a little bit of a substitution of the CH2 with the oxygen from the phosphine reagent, okay? So you end up getting an alkene. So like we have made alkenes before, a long time ago when we were doing the, alkene synthesis with dehydrations and elimination reactions. And it was such a pain, like do we get Hoffman product? Do we get Zaitsev's product? We're getting major and minor products. What is more stable? We've got so much issues. Now, no issues. Okay, so you get your alkene, your straightforward reaction, very nice reaction. And what else do we want as an organic chemist? Okay, so what is this reagent? Okay, the Wittig reagent, what is it? So the Wittig reagent is also called Yelid. And the Yelid can be made in the lab, or in some cases, depending on how picky you are, you can also buy it, okay, from the chemical stores. So if you want to make it yourself because you want to have a specific number of carbons, then you take an alkyl halide, whatever alkyl halide you're looking for. So again, usually people use bromides or iodides, no fluorides, okay? So you use bromides or iodides or chlorides also, and then treat that with triphenylphosphine. Now, I'm using triphenylphosphine, but you can also use any other alkyl group, okay? So you can use trimethylphosphine, triethylphosphine. The bigger groups over here, though, it gives you an advantage that your final product that you will get is going to be a solid, okay? Because if you have low molecular weight compounds, then they tend to be liquids. Higher molecular weight tends to be solids. So it's nice to work with solids sometimes. And so, triphenylphosphine, easy to get and then easy to use. So you create the first part and then you treat that compound with sodium hydroxide, which abstracts a proton from here, and then you end up getting a CH2. So now I want to just point out one thing real quick, and that is this electron pair. So generally when we write our Yelids, okay, we write them like this, okay? So you will try to avoid writing them like this. Do not write like this, okay? Because I do not like that. And also it's not appropriate. Why is it not appropriate? Is because the carbon actually has a pair of electrons there. This one doesn't show that. Okay, it shows that the carbon is bonded. So where is that pair of electrons? Because remember, we're talking about carbons as in carbon nucleophile. So if it has to be nucleophile, it has to has those electrons. The way it is written would seem that you have a minus charge, and that's it. That's one electron, extra electron. But it has two extra electrons. Okay, so make sure you draw a pair of electrons. So it's kind of like a carbene, but not exactly a carbene, but it is sort of like that. Okay, so you have that pair of electrons. So just write it like that. You will see that I have done the same thing everywhere. Okay, and one thing you have to be careful of in the Wittig reaction, okay, because I know we are used to drawing some things in certain ways. So for example, when we draw a Grignard reagent, this is what we write, right? MgBr, and then this is the bond. And that's pretty normal, which means what? It means your carbon numbers are starting from here, 1, 2, 3. And this is your nucleophile. That's what we do for Grignard. That's not what we do here. Okay, in this case, your first carbon is this 1, 2, 3, 4. 1, 2, 3, 4. Okay, so you kind of have to train your mind for this. Okay, so we like to draw lines for bond, but you're going to resist it. Okay, and write the lone pair of electron, because it will also help you. I am not opposed to numbering your carbons. I always encourage that you number your carbons, because then you make sure that you don't lose any carbon in the reaction then. Okay, so here also 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, so number your carbons so you know that you've attached the right number of carbons from your reagent. But make sure you draw the lone pair of between the phosphorus and the carbon to show that this is the carbon, that is the one. I'm going to make this an arrow now. Okay, but this is the carbon that has the nucleophile. You need to also make sure that you're attaching the right carbon to the right thing. I mean, I get weird answers sometimes that you will have the reagent here, but you're attaching it from here, and I'm like, what's going on? So don't have weird things. So these kind of numberings and the electrons and the charges, they help you focus on how the bonding is supposed to take place. Okay, so number if you need to, but that's kind of what's going on here. Okay, with the Wittig reaction is, first of all, you generate the Wittig reagent, and once you have your Wittig reagent, then all you need to do is react it with the whatever you need to, aldehyde or a ketone, in order to get the alkene. Now the alkene, there's only one drawback to this. This can be cis or trans, okay? Because this one has no preference in reacting one way or another. But the one problem you don't have is whether you're going to have a major or a minor. For Hoffman or Zaitsev, you don't have any of that issue there. And depending on what kind of alkene you choose to make, you may not even have a cis or trans issue. Okay, so you can minimize some of those problems, okay, for yourself. But otherwise the reaction is straightforward. Just remember to remove the oxygen, okay, and add the carbons in there to get the alkene. So here's the mechanism for the Wittig reaction. If you don't want to memorize it, you don't have to for me, but otherwise I've given it to you because it's kind of interesting. So here is the yelid, which is the Wittig reagent, and then once you have the Wittig reagent, that will react with the carbonyl, and you end up forming something like this, okay, with an oxide, okay, and the phosphorus, which is positive. Then that gives you a square kind of an intermediate, which is called betaine. This mechanism has been studied to death, and so it's not like we don't know this. Everybody knows this one, that this is how it's going to work. So there's no mystery left for Wittig reactions, and then you end up getting the alkene here after these bonds break, and then here this is phosphine oxide, and that's it. So it's a very straightforward, very nice reaction. I've done this a gazillion times and it works beautifully with really good yields also. Okay, so great way of making an alkene. Again, I've color coded it to show you what groups are coming from where. Okay, so where everything is. So here retrosynthesis, of course retrosynthesis. And how would you make this kind of an alkene? So when you have something like this which is not symmetric, okay, something like this is not symmetric, then when you cleave it, when you break it into two, then you have two possibilities, that one side is the aldehyde or the ketone, the other side is the Wittig, or flip. Okay, so I've done both of this for you. Okay, so on this one, in the first answer, I have the aldehyde on the left side and the Wittig on the right. And in the other case, I have the Wittig on the left and the aldehyde on the right. Now, is one of them better than the other? Not really. It's fine. It just depends on which one is more expensive, that way. Other than that, it should be fine. Okay. So again, I've taken this all the way to halide because that's what the question was. So the aldehyde and the I guess there is no ketone in this one. So the aldehyde is fine, and then the Wittig reagent itself, for that you need to start with this alkyl halide, okay, in here. Sometimes when I give you these kind of reactions, I actually start with triphenyl phosphine, okay, that we're starting with this, and here is your alkyl halide. What do you get? And now you're treating this with an aldehyde or a ketone. Now what do you get? So you're making the Wittig reagent over here yourself, okay. So this could be a part of a reaction, which means what I'm trying to say is you have to know how to make the yelid. And I think that's all there is in this one. Moving on, addition of ammonia. So now we've finished with carbon nucleophiles. So getting into the nitrogen nucleophiles now. These are interesting in the sense that here you can have addition reactions also, but really again this is kind of a substitution going on, okay. So even though these are strong nucleophiles, you're not getting an addition, you're getting a substitution, okay. So here if you see what's going on is that you have an aldehyde or a ketone. You're treating it with ammonia. We will treat it with all sorts of amine derivatives, okay. So we'll start with ammonia. So you start, you react this with ammonia and you end up getting something like this, which means the double bond is retained. With the ammonia, you have three hydrogens. Now you only have one hydrogen. There's no oxygen also over here. So what happened to the oxygen? Minus H2O. So what happens? Oxygen is coming from the aldehyde or the ketone, and the two hydrogens are coming from ammonia. Okay, so that's what's happening over here. The mechanism here is just to show you that how things are working. Again, don't get distracted by the blue arrows. They're just, I don't know why I was into blue arrows when I was drawing this out, but the main thing I want to show you is where the water is forming. Okay, so the minus H2O right here, that's where it is supposed to be. This water, I don't even know why I have that, so I'm going to go ahead and cross it out because I don't think that's needed there. Okay, so excuse me. And so then here, this is how you lose water, but this reaction you need water also. Okay, so it's not like this is happening just by itself. But you do generate the oxides here. Okay, so which means that this is not an acidic mechanism. In any case, this is the formation of what we call imine. Okay, so when you react an aldehyde or a ketone with ammonia or any of the nitrogen derivatives, you end up getting imines. So here are a whole bunch of other imines you can form from the ammonia derivatives. Again, color coding here for you a little bit. So here is the nitrogen, right? Here's the oxygen. Okay, so this is the carbonyl, and once you add the nitrogen to it, this is where it goes. You need to have the two hydrogens because you need to remove the water. Okay, so in all of these, you will see that I have the NH2, 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 NH2. Okay, what is different is this, the Z. That attachment can be hydrogen, can be any R group, can be OH, another NH2, whatever. It can be anything, okay? And according to that, your products will change as well. You will always get rid of water. Where is that water coming from again? These two hydrogens, okay? That's where it's coming from. So whatever that third group is on the nitrogen is what's going to stay. All right, so in the case of a primary amine, the two hydrogens are there, but the one R group, that's going to stay. Okay, in the case of hydroxylamine, you still have the two hydrogens, and here you have an alcohol group. That alcohol group is going to stay. Okay, this is hydrazine. You've seen hydrazine before in Wolff-Kishner reduction, and hydrazine is NH2NH2. So in NH2NH2, you have these two hydrogens that will go away, and then these two nitrogens will stay. Okay, so that's kind of what happens with all of these derivatives. Okay, is that you have the two hydrogens that go away with the water, and then whatever group is there will remain. Now, do you need to remember all these different names? No, you don't have to. My thing is that you just remember them as imine. Okay, that's good enough for me right now. If you remember that this is an oxime, that's great. I don't need you to. Okay, I need you to be able to write the reaction and recognize that this is an imine. Okay, or this is coming from an aldehyde or a ketone and an ammonia derivative. That's what I need you to know. So all of that was primary amines, okay, the NH2, right? The NH2 was all there. Now, if you treat something with a secondary amine, so here is a secondary amine, okay, where you have two alkyl groups, but only one hydrogen. So remember what has to come out? Water has to come out. So if water has to come out, and if you're treating something with secondary amine, where is the second hydrogen coming from? The second hydrogen comes from the alkane. Okay, and so here is the alkane, and then the alkane group, I should say. Okay, so you have the oxygen of the carbonyl, and then one of the neighboring hydrogen goes away, so water. So what do you end up getting? You have the nitrogen with the two alkyl groups, because those two are not going anywhere, and then you have the double bond here. Okay, so these are called enamines now. Okay, so enamines, and I will write it again later on, but right now I'll just write it for you. So an enamine is where you have the double bond, and then you also have the amine group, okay, in here. Note, what you don't have over here is the double bonded nitrogen. Okay, the nitrogen here is single bonded, it is not double bonded. So this is not an imine, this is an amine, okay, but you have the double bond of the alkene, so it's enamine, okay, for that reason. So a couple things over here, okay, to note that here, first of all, this is a secondary amine that you need, and the other thing is that you will always form a Zaitsev product, okay. So here I took this compound to show you that if you have two hydrogens available, which there was a hydrogen available here also, but this will not go, okay, because that will give us the Hoffman product. So we want to make sure we get the Zaitsev product, okay. The more stable alkene is what you end up forming, and so you end up getting an enamine like this, okay. So this is with secondary amine. Tertiary amines don't react with aldehydes and ketones because there is no hydrogens, okay, for us to eliminate. Okay, so this is hydrolysis of amines, and what this is telling you is that the formation of an imine is also in equilibrium. I didn't point it out before, okay, but this is also in equilibrium, which means it can go back and forth, which means you can take the imine and convert it right back to aldehyde or a ketone. Okay, so these are all the reversible reactions for it. So I've shown you how you can do hydrolysis. So all you have to do is kind of break the bond at the double bond. Okay, so here is the imine. So when you cleave that in presence of acidic hydrolysis, then you end up getting your amine back and the aldehyde or the ketone back, okay, depending on what it is that you're reacting with. And I think here I have a small issue. I always have issues. Why do I always have issues? But I do, okay, because this one should be a hydrogen, okay, over here, because this is a hydrogen. Okay, so that should be a hydrogen. That's not a ketone, so that's an aldehyde. So anyhow, other than that, everything is fine because here is the pH and then the nitrogen group, okay, and then the two carbons. So that's that. So just cleave it at the double bond, and then you can write your nitrogen group and the aldehyde or the ketone, okay, on the double bond. Okay, so a couple of the specific reactions for amines, okay, for reaction with aldehydes and ketones is the one that I wanted to mention here is the Wolff-Kishner. The Wolff-Kishner reduction is when you take an aldehyde or a ketone treated with hydrazine followed by potassium hydroxide to give you hydrogenation, completely reduced. Okay, so now the oxygen is completely gone from there. So we've done this reaction before in aromatic chemistry, but here, I mean, it's not an aromatic chemistry reaction. It's actually an aldehyde ketone reaction. Okay, so you can do this with any aldehyde or a ketone. So this is Wolff-Kishner reduction, but again in two steps this time. Okay, we did this in one step, like we wrote everything together. Okay, the first time. And the second reaction I want to mention here for you is the qualitative test that we do for aldehydes and ketones is using this compound. This is a huge compound, and this is called dinitrophenylhydrazine. So again, you have this hydrazine thing over here. So this is going to react with the aldehyde, the ketone. And because this is so bulky, you end up getting a solid at the end. Okay, this is orange. So the product is also generally orange, but that's not the qualifier. The qualifier is a solid, okay, or cloudiness that you end up seeing. That is the qualifier for a positive test for an aldehyde or a ketone, okay. Orange color you will still get even if you have an alcohol, okay, because the color of the diphenylhydrazine is itself orange. So two reactions that are really interesting over here for amines. Yep. Okay. And then finally reduction. Okay, that's the last nucleophile, and that's the hydrogen nucleophile. So reduction of aldehydes and ketones, both of them can occur. Now, in both cases, you can use a weak one or a strong reducing agent. So weak is sodium borohydride and a strong one is lithium aluminum hydride. You can use either of those. Just remember that an aldehyde is a terminal group. So when you reduce it, you get a primary alcohol. And with ketones, you end up getting a secondary alcohol. You cannot make a tertiary alcohol this way because of the nature of aldehyde and ketone. But you know, that's primary and secondary is still quite good. Okay. And you can use any kind of reducing agent. Here also, you can use LAH if you wanted to, depending on, you know, what you have. You can also use hydrogenation if you want to. The only thing you have to remember is if you're using hydrogenation and you have a double bond, that double bond will also go. Okay, and that's the thing about reductions you have to be careful of, especially with hydrogenations. Hydrogenation is such a powerful thing that you can reduce everything, okay? But reduction like this, you know, hydrogenations, you know, they are done under high pressure and all that. So generally, if you're using hydrogenation, it means that you want to get rid of the double bonds also, okay? So if you have something like what I have here with a keto group and an alkene group, and you just want to reduce the ketone, then better to use sodium borohydride. Okay, don't bother with hydrogenation, just use this. So if I were you, I would not use hydrogenation as your reducing agent for most part, because you might forget that you have an alkene somewhere or an alkyne somewhere. Okay, so try to focus on the aldehyde and the ketone if you're reducing just that. And just use, you know, one of these two reagents, okay? Because hydrogenation will reduce everything. It will reduce any other group also, okay? So there's no point using hydrogenation as your reducing agent. Unless you want to reduce everything, that's different. Okay, so here are a couple other reductions, and these reductions are not necessarily using sodium borohydride and all that. So Wolff-Kishner you already know, okay, because that's hydrazine. We just talked about that. So that's one reduction, and then Clemmensen reduction also you have done. This is done in presence of an acid, but it's the same thing. You can reduce an aldehyde or a ketone all the way to an alkyl group. Okay, so again, just complete removal of the oxygen. So both of these reactions, they're very good in removing the carbonyl group. Okay, so again, this is not a new reaction. You've done this before. And finally, oxidation. Okay, so oxidation of aldehydes. Aldehydes, remember, are terminal groups. So aldehydes can give you only acids. Aldehydes are in the middle, right? So you can go from an alcohol to an aldehyde to an acid. Okay, so that is your general route, okay, from going from one series, I should say, to go from one to the other. So here we are right in the middle. Okay, so aldehydes, you can only oxidize them to give you acids. So that's what we have here. So you can use strong oxidizing agents. You can't use the weak ones because you're going all the way now, okay, all the way to the end. So you need a nice strong oxidizing agent. So KMNO4, chromic acids, these are usually going to be favorable for oxidations. So, very good oxidizing agents. I mean, they are a little toxic, but other than that, they're pretty good oxidizing agents. So you get carboxylic acid. And the tolerance test, this is an interesting one because this is for aldehydes, of course, because aldehydes are the ones getting oxidized. So if you take any aldehyde and treat it with silver nitrate and ammonium hydroxide, you end up oxidizing the aldehyde to the carboxylic acid, which is fine. But in the process, you reduce the silver. So silver plus 1 goes to silver, and then this is a solid. Okay, so silver nitrate is in solution, but this silver precipitates out. And once it precipitates out, it forms a beautiful mirror, that's why it's called the silver mirror test also. So tolerance test or silver mirror test, same thing, is it gives you a nice precipitate of silver at the end, and that is the qualifier that you have an aldehyde. Okay, so we learned about the test for aldehydes and ketone, which was the DNP test, which is the dinitrophenylhydrazine test, but that doesn't distinguish between aldehyde and ketone. To distinguish between aldehyde and ketone, you can do the tolerance test. Now, the tolerance test is also an oxidation reduction, right? Reaction, not reduction, sorry, oxidation reaction. So, but this is not a very good way of oxidizing aldehydes. If you want to oxidize aldehydes, you would want to use something cheaper. You don't want to waste silver, okay, for that. But anyhow, this is a good qual test, okay, for aldehydes. So oxidation of ketones. So ketones generally are not favored to be oxidized, but they can be in some instances. So the first oxidation is the Baeyer-Villiger oxidation, which when you take a ketone, treat it with a peracid, peracetic acid or anything like that, MCPBA, then you end up getting an ester. Okay, so you don't get an acid because ketones are internal groups. So you end up getting an internal group as well. Okay, but that's all I'll cover for this one. And then if you have a methyl ketone like this, then it's a very specific reaction. So if you have a methyl ketone like this, or if you have acetone, then you can oxidize this methyl group. So by treatment with sodium hydroxide and potassium iodide, and you end up getting an acid. Okay, so even if you were working with acetone, it will do the same thing. Okay, so you can take this same reagents. So if you have sodium hydroxide and potassium iodide, you end up getting acetic acid in that case. Okay, and so you are getting an acid, but it's not a very good way of making an acid because there are so many other ways you can. But this is a very good qualitative test for methyl ketones. Okay, so very specific. This is acetophenone, so it has a CH3 group, and acetone has a CH3 group. So it's a very good qualitative test for methyl ketones, because what happens is that you get the acid, but you also end up forming a beautiful yellow precipitate from what is called the iodoform. So this is also called the iodoform test. Remember CHCl3, this is called chloroform. So this is iodoform. And so you end up forming iodoform, which is so heavy because of iodine, and it's actually a solid. Okay, and so this iodoform test is used generally in the lab to figure out if you have a methyl ketone or not. Okay, so it's not particularly a reaction used for oxidizing, but that's the reaction that is happening in there. So otherwise ketones, really you can't do a whole lot much more, okay, with ketones. Here are all your qualitative tests for aldehydes and ketones. You can read them through. The reason we kind of go through all these qual tests is when you do spectroscopy, okay? Because sometimes when in spectroscopy you're trying to decipher a structure, we can give you clues as to what the functional group might be, okay? So for example, if we say that, oh, this compound is giving a positive, for iodoform, then you already know that, okay, I have a methyl ketone somewhere, So it kind of helps a little bit with all of these. So it's kind of nice to know all these qual tests. And these are all reactions you're doing anyway. Okay, so let's carry out the following transformation. And here is our starting material, just a methyl cyclohexane, and this is our product. So we're adding a carbon with a double bond, so an alkene. And the way we can do this is, of course, by carbon-carbon bond formation only, because you're adding a carbon. So the two ways that you can do that is by Wittig and Grignard. Okay, and so let's take both one at a time. And so here is the first one. So to get anything done on any kind of an alkane, the only thing you can do on it is do a free radical reaction to add a bromine. Once you have a halide, then you can do whatever you want, substitutions or eliminations. We'll do elimination to get a double bond Y, because we need to activate this carbon. We need to put something over here. And so here we're going to put the alcohol, because we need to add double bond over here. Okay, so we need to add an alcohol because we need to have a keto group over here for Wittig. So hydroboration will give us the anti-Markovnikov addition on this alkene. So we get the alcohol, oxidize that alcohol to give ketone, and then do the Wittig to get our double bond. Okay, so pretty straightforward kind of a reaction. Let's look at the other one, what we can do, if we can use Grignard or not. So here we are doing this. So you get the bromine, same thing, no problem, double bond, no problem. But now instead of getting alcohol, I'm going to go ahead and add a bromine in order to make my Grignard. So here I'm going to use HBr with peroxide, because that's what gives me anti-Markovnikov addition for brominations. So here I have bromine, add magnesium, get the Grignard, and then add formaldehyde to get this alcohol. So now I have to dehydrate this in order to get my alkene. So all of this is fine, except for the last reaction. This is not fine. Okay, and so this is a little bit of an issue, because usually if you first of all, you can't dehydrate primary alcohols. This is a primary alcohol. So to dehydrate primary alcohols, you will end up getting rearrangements, okay? And so which means if you think about the mechanism, you will generate a carbocation here, which can then rearrange to give you a carbocation here, which is more stable, which means that the double bond will form here inside, not outside. So clearly we can see that this reaction is not going to work very well. Okay, and if it does, it will probably involve a little bit more steps, but everything was going fine until we got to the last step. So essentially this is the only way. So I'm just writing the other one to show you that sometimes it seems logical that, oh yeah, I can do a dehydration, I can do all of this, but sometimes it doesn't work. Okay, and sometimes you just have to write out the synthesis in order to see that, it may or may not work, whatever it is. So for us, I think, the only one that works well for us is the Wittig reaction, okay? So the top one is the better one. I'll leave the bottom one there just so that you can see some of the reactions you can do depending on what we were doing, but this reaction, the last step, is not going to work for us. Okay, and I think that's it. So all of the things that we have done in this one, please make sure you go over everything. Again, I have not done the mechanism for Grignard here. You can go back to the alcohol video to look at the Grignard reaction mechanism, but all the other stuff I have given in this. Okay, so it's a lot of reactions, I know.